Hello. Hi. Good evening, everybody. Am I audible, video visible?
Yes, ma'am.
Okay, great. So, I'm just sharing. Okay, all good. Screen's also visible.
Yes, ma'am.
Thank you for confirming. Yes, so once more, good evening, everybody, and welcome to today's tutorial on urban utilities planning, water supply, sanitation, and drainage. So today we will be discussing some of the assignment questions and some problems which we saw in week 9. So I hope all of you have seen week nine's lectures. So we'll be discussing some questions regarding week 9. So these are the topics which we covered in week 9. In week 9, we went into the details of sewer design. So as discussed, this course has got three parts: water supply, sanitation, and sewage. So the last part, we are coming into the last part towards our last lecture. So this is a 12-week course, so we just have a few more weeks left. So these were the five lectures we mainly saw into sewer design. In sewer design, we went into what are the assumptions of sewer design. So we're seeing that there were three main assumptions which we follow. We usually assume that the flow is steady state and there is not much turbulence inside, and we also assume the flow is along the pipe, so there's no other turbulence which are created inside, and we also assume that there's a self-cleansing velocity. There's a self-cleansing velocity which needs to be attained, and at least this is attained at least once a day, so that the sewer is completely cleaned and there are no siltation or any blockage inside the sewer. Then we also saw how do we calculate the self-cleansing velocity. Then we saw different types of sewers, the broadband which needs to be kept open channel, closed, different types of sewers. Then in that again, we also saw how are their gas buildups. So we looked into all these details, like if there's H2S buildup, how do we remove it? What is the method that is used, and what is the velocity of flow that needs to be there in order to remove such buildup? Then we also saw into how do we design sewer. So that's when we came to runoff estimation. So we saw while why do we estimate runoff is so that in a combined sewer we have to design sewers. So that in the last week's lecture also we saw on how do we design combined sewers, what is the assumption that we take, what is the empirical formula. So we broadly saw what are the different methods, but then we went into details on what are the different methods we use. So we use catchment routing method, time area method, uh, assuming when the pipe is flowing full or when it's partially flowing, how do we. So based on this, we saw different calculation methods also. How do we assume find the runoff, and how do we design the diameter of our sewage considering both sewage and runoff, stormwater runoff. Then in the last two lectures we saw how do we design sewerage networks. So what are the different kinds of networks, how do we join them, all those details we saw in these lectures. And we also towards the end we also saw what are the different sewage maintenance methods that needs to be used. Preventive maintenance, how do we plan for maintenance beforehand itself, or do we, is it a post deterioration maintenance or is it a pre-deterioration maintenance? So all these we saw in details. So now we will get into some questions and we'll try to solve these questions. So I think most of you have been there. I see one new face. So this is how we will be going. Like we'll go question by question and we'll have a 5 minute discussion, 5 to 10 minute discussion towards the end of all the questions for any other doubts. And if you have any doubts for that particular question, you can immediately ask. So I think it's known to all of you. So we'll just go into the first question. So first question asked, self-cleansing velocity depends on A, particle size, B, gravity of the particle, A, particle size, gravity of the particle, conduit shape, B, particle size, conduit shape, depth of flow, C, specific gravity of particle, conduit shape, depth of flow. 1 minute. Yeah. And D, particle size, specific gravity of particle, conduit shape, depth of flow. So there are multiple aspects which are given. So yeah, can somebody attempt this question? Okay, before we begin, what is self-cleansing velocity? I just briefly explained in the introduction. So, can somebody elaborate on what is self-cleansing velocity? We have a good strength today. Somebody should be able to explain this. Okay, Jivanshu, do you want to give it a try?
I think the velocity which um, there'll be no deposition or some accumulation will not happen. The
Okay.
velocity which help, so that is self cleansing velocity.
Okay, yeah, very good, very good. That's the answer. So, it's the velocity in which, so we design a sewer. So we have the diameter of the sewer. So we design in such a way that the flow through that sewer is, or the velocity in which the flow happens is adequate enough in order to clean the sewer. Or if there is some deposits, then because of this rushing stormwater or sewage effluent which is moving through that sewer, these deposits will be washed away. So that's why it's called self-cleansing velocity. And how diameter, so when we reduce the diameter, so we know that when the volume like Q is equal to A by V, so we have seen this, or V is equal to QA, so we get all these relationships are there. So based on that, based on the volume which is flowing, you can adjust the area so that you get the self-cleansing velocity. So that's what we, in the introduction also we saw. We even saw what is the formula which we need to use in order to find self-cleansing velocity. So it goes something like we have V is equal to 1 by n r raised to 1 by 6 k raised to. So we saw a formula something like this. So this is usually used when we have so many variables. So we consider all these aspects and we design on what should be the velocity in which the water should be flowing so that the sewer is cleaned by itself. So as rightly said by Partha. So what are these parameters? So in these formula, we consider certain parameters. So what are these parameters? That's what the question asks. So do we consider the particle size, specific gravity of the particle, conduit shape? So I think most particle size and what is added over here. Yeah. So here depth of flow is also added. Then yeah, that's it. So these are all the variables which are there. So you have got particle size, specific, so one particle size, specific gravity of the particle, conduit shape, and depth of flow. So now these are given in different forms in the different combinations are given in the answer. So, okay, so any attempts? Anybody wants to attempt this question?
Option D, ma'am.
Option D, particle size, specific gravity of particle, conduit shape, and depth of flow. So you're saying all of them
All of
matters.
yes.
Okay, very good. So let's see how each, that is the right answer. All these play an important role. So let's see, this is what we saw in the lecture. So we mainly use this formula called Shields formula. This is what I was trying to explain before. So where you have this V is equal to 1 by n, r raised to 1 by 6, root of ks s minus 1 dp. So in this you see your n is the Manning's coefficient which is there. Now r is your hydraulic mean radius. So hydraulic mean radius we've already discussed. It means area by wetted perimeter. So if you look over here, in the depth of flow is included in this because when you're talking about wetted perimeter, you're mainly talking about the depth in which it is flowing. So if you have a conduit like this, and if you have a sewer like this, and if it is, so in this one, if there's q quantity of effluent which is flowing, probably it will only be half full or maybe a bit less than half. So which means the wetted perimeter becomes only this much. Whereas if you're using a smaller one, maybe it is 3/4 full. So your wetted perimeter changes. So this factor, your R factor, which is used over here, will change based on that. Then next one, yeah. So Ks is a dimensional constant. And how do you get this dimensionless constant? You get it about the start of motion to the granular particles of about 0.48 for adequate step. So it's again, it depends upon the motion of the granular particle. So you get it based on that. Then you have S, which is the specific gravity of the particle. So that is what is asked over here. specific gravity of the particle. Does that influence? Yes, the specific gravity of the particle is also a part of this. And finally, D, which talks about the particle size. So that is what was there in the first one, which is particle size. And of course, the conduit shape as discussed. So this we discussed in terms of circular sieve. Now imagine you have an egg-shaped sewer. So this we discussed in our previous. So the advantages of having an egg-shaped sewer is that I'll draw it here. So when you have a higher velocity flow, then a higher diameter is taken. Like it is capable of catering to that much flow. But when you have a low velocity flow, again water can flow through this small region. So because it is egg-shaped or because you have the bottom portion curved a bit more, it is capable of carrying more, like it is capable of attaining more velocity. Whereas if it was a circular sewer, then probably it would flow something like this, which means the area is more or it's more spread out, which means the velocity won't be adequate enough. So the shape of the conduit or the shape of the sewer also influences the self-cleansing velocity. So is that clear? Everybody, shall we proceed to the next question? Yes.
Yes, ma'am.
Yeah, thank you. So we'll go to question. So this question has got two parts. Question 2 and 3 has got two parts. So let's see. The sewer is laid in 1:600 slope. The diameter of the sewer is 150 centimeter. So we have a sewer which is of diameter 150 centimeters. So let's say it's okay, 150. Yeah, so we have 150 centimeter. We'll convert it later. Then we have Manning's coefficient, which is given as n is equal to 0.015, and the sewer is running half full. That is what is given in the question. Now, this is the basic data which is given. Now, the question 2 asks, what is the velocity of flow in the sewer? So, as we discussed, based on the diameter of the sewer, based on the slope of the sewer, the velocity changes. So now the question asked, what is the velocity in the sewer? And they've been asked to find it to two decimal places. Okay, so let's see what is the information which is given. So we have the slope, which is 1:600. Then we have the diameter. So diameter is given to be 150, so 1.5 meters, converting and writing 1.5 meters. N is our Manning's coefficient, which we saw before. So that is 0.105, that is also given. And the sewer is running half full. So where this is useful is, so let's see. So what equation will we use over here? Sewer is running half full and we need to find the velocity. We have done a similar problem for water supply. So which equation will we use? Yes. Manning's equation? Can we use Manning's equation?
Yes, ma'am. V is equal to 1 by n.
1 by n.
R2 power 3.
Very good. And
S1 power 2.
s raised to 1. Yes, very good. So this is Manning's equation. So we can use this here. We also learned one more equation, Hazen-Williams equation. Can we use that over here? Yes, no?
I'm not sure, ma'am.
Okay, yeah. So Hazen-Williams equation is also used to find the velocity. So we can use Hazen-Williams equation provided the sewer is running full. Like in water supply, we have learned this, that if you have the pipe and if the water supply drainage channel is running full, then Hazen-Williams equation can be used. But when it is only partially full, then we need to use Manning's equation. Manning's equation can be used for full flowing flows also, but so it's an alternative. Hazen-Williams equation is an alternative which can be used for full flowing. But for sewage design, so we don't design our sewers to be full flowing. We never design the sewers to flow full. It is always only partially full. So in the lecture, we might have seen that it again depends upon the population. So for population and also based on the diameter of the pipe. So in case we have a 75 diameter pipe, then we assume that the sewer, maximum sewer can be around 2/3 full. And if the diameter of the pipe is around, let's say, I think, 50, if it is around 53rd, I'm not remembering, 35, I think. Okay, for another diameter, we assume that it is only half full. So if it is more, no, if it is less than 75, sorry. If it is less than 75, we assume that it is two-third full. And if the diameter is more than, sorry, less than 75, the diameter is more than 75, we assume it is flowing only half full. So like this, we assume also based on based on the diameter, based on population also, we assume how much full. But the whole point is that we never assume it to be fully full, or we don't design the sewer to be fully full, because because if the sewer is fully full, then it is very difficult. Like it's not like the water supply channel, right? These are effluents. It has some solid particles also which are there mixed in it. So you need the self-cleansing velocity. So for all these aspects put together, we don't design the sewer to be fully full. But in your questions, assignment questions, gate questions, even in your exam questions, maybe you might get problems where they're saying that assume the sewer to be fully full. So these are mainly done for calculation purposes, but not for practical purposes. So yes, so why I said this is because we are using Manning's equation over here, mainly because it is mentioned that it is running half full. So now here, yes, so this is Manning's coefficient. Now this one, R is the hydraulic mean or hydraulic radius, which we get. So I'll go to the next page. Yeah. So R is equal to your area by wetted perimeter. So we need to find that, and S is a slope. So which is already given. It is given 1 is to 600, right? Yeah, 1 is to 600. Now this one, if you do, it is half flowing foot. So area will be pi d square by 4. Area is pi r square. So pi d square by 4 divided by, now area will be pi d by 2. Pi d is the actual area, but your wetted area means it's only flowing half. So it'll be pi d by 2. So this would be d by 2. If the flow was full, then it would have been d by 4, because again,
Therefore,
yeah, if it was so full flowing, it will be d by 4. For half, it is d by 2. Okay, so this is what we will be using over here. So let's put this in the formula. So V is equal to 1 by N is 0.015 into R. R is d by 2. So again, what was our d? D was 1.5. So 1.5 by 2, that is 0.75 meters. So 0.75 into, sorry, raised to 2 by 3 into our 1 is to 600 slope. 1 is to 600 raised to 1 by 2. Okay, so how much does this come out to? Yeah, done?
ma'am, 1 minute, ma'am.
Okay,
Calculating.
okay.
1.08 meter per second.
Okay, let's see. How much did you get this one as? 0.75 raised to 2 by 3? I mean, that's not the answer, so maybe you're going wrong somewhere in the calculation.
That is 0.825.
0.75
By
raised to,
3 is 0.825.
okay, correct, 0.825, yes. And this one, did you use the brackets correctly for that? Just check.
Ma'am, it's 2.24, ma'am.
2.24, correct. 2.246 something, it just keeps going that way. It would be around 2.246 something, so we can approximate it as 2.25. Okay, everybody with me? Aishwarya, did you get this answer?
So I'm still doing.
Okay. Fine, just complete this then, because next, otherwise, it'll be lagging. Vaishaka, you good? You got this answer?
Yeah, ma'am, I got the answer.
Okay, very good. And Yatika?
Hi, ma'am. I'm just doing it, abhi
Okay.
to.
Okay, fine. Yeah. Okay. So let's proceed. So this is what, so you can continue from here. This calculation will give you V is equal to this much. Now the next part is, what is the question want us to find? Let's go back to the question. Question is asking what is the velocity of flow in the sewer? So that part we have got. That is this velocity of flow in the sewer. So options are not given in this, right? Yeah, there's no option. So yeah, so you will have to write the answer as 0.25. Like, so yeah, so they said rounded off to the two decimal places, so we can round it off as not 0.2, 2.25. So that's the answer for this one. Now the next question. What is a discharge flowing through the sewer? Again, hint, enter the answer to the two round. So this was a format which was given for previous assignments, but I think this assignment onwards, this format is not there, right? Where you have to enter the answer. It's only multiple choice answers. But also look that you round it off so that maybe otherwise the options might not match. So yes, so we know we have velocity. So we know that B is equal to Q by A. This we know velocity is equal to volume by area, or Q is equal to VA. So we have been asked to find Q. So Q is equal to VA. This we know. So yeah, you have been asked to find discharge, which means you're finding Q. So velocity, we already got it as 2.25. So we can just put it there into now area. What will the area now be? So do you take the whole area of the sewer, or we'll only take half of the area of the sewer?
I think half.
Half, because it is only flowing half full. So when we want to get the actual discharge, we need to take the actual volume which is flowing, means the actual volume, right? So that means it's not flowing full, so it's only half. So you take half of the area. So your half of the area is equal to half into pi d square by 4. So where d is equal to your 1.5. So you can just put this here into 3.14 divided by 4 into 1.5 the whole square. Yes. So how much does that work out to?
0.49 meter cube per second.
Okay. Can you check once more? Maybe something is going on.
1.98.
1.98. That is the correct answer. 1.98. So when we round it off to two decimal places, 1.98, 1.99, because after 8 again there is something which is there. So 1.99, both are correct. Depends on what is there in the option. Okay. Any doubts in this question?
Can you show the question once? I'll take a screenshot.
This question. Oh, okay. Yeah. Okay. Shall we proceed to the next question?
Yes, ma'am.
Okay. So question 4, 5, and 6 again, it's a numerical. So we'll start. So the data which is given is, consider the following data. It's a circular sewer of diameter 50 centimeters, slope 1 is to 220, and n. Okay, so this is the next one. N is equal to 0.015, which is a Manning's coefficient, and flow is full. So previous one flow was half, now flow is full. The question 4 asked, what would be the velocity and discharge of flow in meter per second and in discharge in meter cube per second respectively. So our question 2 and 3, it's combined into one. Question 4 itself is asking both. So I think this you can easily do because we have already solved this. So I would say do, and we'll discuss the answer.
Question once, ma'am, for data.
Sorry, take, yeah. So data will just write diameter is 50 centimeter, which will be 0.5 meter. Slope, which is our S, is 1 is to 220. Then your Manning's coefficient is 0.015. Okay? And the flow is full. Data done. Okay?
Yes, ma'am.
Okay.
Velocity is 1.123.
Correct. Velocity is
And
1.123.
discharge is
1233 it goes. So, uh, yeah, 1.123 itself. Correct. Yeah, so now you can find discharge.
discharge is 0.22.
Discharge is 0.22. I think from, yeah, 0.22. So discharge Q is equal to V into A. V is 1.123 into A pi d square by 4. So where D is your zero point 0.5. So we'll just substitute into 0.5 the whole square divided by 4. And yes, this works out to 0.22 meter cube per second. This is meter per second. Yes. Okay, very good that you're able to solve this in class itself. So, how about the others? Aishwarya, are you still calculating?
Yeah, I got it, ma'am.
Okay, very good. Vaishaka?
Yeah, got the
Okay. So,
0.22.
Yatika also done.
Yes, ma'am.
Okay, very good. Awesome. Fine. So, we can proceed then. So, this was the first part where we were asked to find what would be the velocity and discharge. Okay. So, I hope there's no doubt in this. I mean, all of you have got. So, now comes the next part. What would be the velocity and discharge when the same is flowing at zero point 0.3 of its full depth? So which means it's only 30 percentage. 0.3 means it's 30 percentage. That's what. So before it was, so when you say full flowing, which means it's 100 percentage. Half flowing, it is 50 percentage. And now 30, 0.3 means it's 30 percentage of the full depth. How do we go about this? Do we go back and find the R by using area by wetted perimeter? and then substitute and then continue? How do we go about this question? Anybody? Okay.
I think based on discharge we can get it.
Based on discharge. Discharge is Q. So we have already found Q. Based on that, we can get this. So they've asked to find both velocity and discharge when the same is flowing. So basically the idea is before we assume that it is flowing full, as discussed, sewage lines never flow full, but for calculation purposes, it was given that it is flowing full. And now it's said that it is flowing only 30%. So and it's saying if it is flowing only 30%, what will be the velocity and discharge be? Which means the pipe is the same, like, or the conduit dimensions which were given in the previous question is the same. So we know that D is equal to 0.5. Then what else was given in the question? Slope is given 1:20. Manning's coefficient is also given. That is all the same. So S is equal to 1:220 and N is equal to 1 by 0, sorry, 0.015, like 1 by we take it. So this information is there. It's fixed. The only difference is that now it's only flowing 30%. So what is changing over here? When the flow changes from 100% to 30%, if you look at the Manning's equation, 1 by n into r raised to 2 by 3 s raised to 1 by 2, what is changing? Like s is not changing, n is not changing. What is changing is r. R is the only one, only thing which is changing over here. Why? Because you have a wetted perimeter to find r. So now the wetted perimeter will change because it was only flowing 30%. So the crude method would be to go back and then find what is, sorry, I went, yeah. So the crude method to go back, find what is R and then find this. But that is going to be very difficult because now how do you find wetted perimeter again? Because you have the whole thing now only 30% means how will you find this perimeter? Again, you will have to divide the whole circumference into proportionally, you will have to divide and then find. So it's not impossible, it is possible, but it's tedious. And when we know that in the sewage flow, this is a very common phenomenon. Like it can be flowing 30%, it can be flowing 70%, 75%, it can be flowing 50. So that this percentage keeps varying, right? So for every time, it's not possible to go back and do the calculation in order to find what is the velocity or what is the quantity which is being discharged through this conduit. So for this matter, based on these proportionalities. So if you look, this is always a proportionality, right? Based on like this much portion it would be like this is 30%, which means the perimeter would also vary this much. When you're finding the discharge, again, the area in which water is flowing is only 30%. So again, it keeps varying. So it's a proportionality. So based on this, we have so based on this Manning's equation, these proportionate curves have been drawn. So a curve has been plotted for proportionate area, then for proportionate discharge, one curve has been plotted, proportionate velocity, one curve has been plotted. So all this based on the proportionate hydraulic element. So over here you have 20%, 40%, 60%. So based on the proportionate hydraulic elements, mind this is only for circular sewer. If it is an egg-shaped sewer, then the whole thing changes. You cannot use it. Why? Because in a circular sewer, again, if it is half flowing full or three-fourth flowing full, then we have, like, we can take those proportional. So based on this, we have developed all these proportionate, so this is the proportionate depth. So it is flowing 20%, 30%, 80%. So based on the proportionate depth of flow, the proportionate hydraulic elements are given over here, which is these factors which are there, and a curve is being plotted for that. So this in a tabular form will look something like this. So we can make use of this data, this tabular data. So this is available in all the handbooks or this is there in most of the standards also. So based on this standard data, we can easily use, we can just find for full 100%, we can get the data and just use these proportionality values and then find. So in this question, they have asked for 30%. So we'll use this one, which is for 0.3. So 0.3, 30%. So we are asked to find, oh, 1 minute. I think my laptop didn't get connected. Just hold on. Okay. Sorry. Yeah. So yes. So we'll be using this one. So we've been asked to find the velocity. So what is given is here is v by v, which means this capital V is the velocity for 100% flow, and the small v is what we are interested to find. And then this is q by q, small q by capital Q. Capital Q is a discharge for 100% flow through the pipe, and q is the small q is what we're interested to find. So two values we are getting, 0.776 and 0.1956. So let's take these values and then find. So we have, like, for let me just rewrite it. So for 0.3 percentage, V by V is equal to 0.776 and Q by Q is equal to 0.1956. So if V by V is 0.776 and V, what is V? We found it in the previous question. Where was it? Yeah. So it was 1.23 and this is 0.22. Let's just write that down here. So capital V is 1.23 and this is 0.22. So now small v will be equal to 0.776 into capital V, which is equal to 0.776 into 1.23. So how much does that work out to?
0.9.
0.9, 0.9, oh, oops. Okay.
0.9.
Everything is running low on battery. Yeah.
444.
0.9, yeah, it's about 0.87 something. So we can approximate,
0.879.
yeah. So you're right, we can approximate it as 0.9, but yeah, the actual value comes out to 0.87 something. And Q will be now 0.1956 into, this is a small q which you're interested to find, sorry, into this one 0.22. How much does that work out to?
0.04.
0.043 something. Yeah, it's good you're approximating. So because it's 3, you can even say it's 0.04. So if you have an option, is there an option that one? Yeah, so in the option, 3 decimal places are given. So we can go up to 3 decimal places also. So yeah, so we have it as 0.873 and 0.043. So yeah, so the rounding off we can do based on the option which is there, or if it's given in the question. So yeah, so this option works the best. Is that clear? Okay, I think a similar question is there in this time's assignment also. So you can check this table and then do. So this was one. Now the next question is, what would be the velocity and discharge when the same is flowing at 0.7 of its full depth? So this I'm not going to do. I think you can do. I'll just show you the table. You can take it from the table and then do. Sorry. Yeah, this is the table. So yes, you can put the answer in the chat box. You can speak it out also if you've got it.
Velocity is 1.257
Okay, very good.
and discharge is 0.159.
0.159, huh? Okay, I mean it's approximately correct, but I am getting it as 0.156.
0.16.
Correct. Yeah, 0.156. So yeah, so it's just minor difference, so it is okay. So yeah, so is that there in the options? I think where's the question? Yeah. So option C, right? Yeah, 0.16. Yeah, so option has again rounded it up. So Yeah, option C. All clear? I think, yeah, three. Any doubts in this question? Shall we proceed further?
Yeah.
Okay. Thank you for that confirmation. Yeah. So let's proceed further. Question 7. The different applications of SWMM include A. Design and sizing of drainage systems of flood control. B. Sizing of detention facilities for flood control. C. Floodplain mapping of natural channel systems. D. Control strategies for minimizing combined sewer flows. What is SWMM? What is SW? You can attempt, like, what? I'm sure you might have seen it somewhere, right? Okay, so SWMM is a software which we used in order to manage, like for stormwater management. So SW stands for Storm Water Management Module. So SWMM. So this module, it has a series of steps. I think it's there in the lecture also, no? Where the software has been shown in detail, where it's shown what is it used for, how is it used for, what are the steps, like periodically what are the different steps which are there. So so the question asks what is the application? So multiple applications are given. Maybe not all are its applications, or maybe all are. So let's go. First one, design and sizing of drainage system for flood control. Is that an application of stormwater management module?
Yes.
Yes. So why? Because the whole idea is that you manage your stormwater. So to manage stormwater, yes, designing and sizing of drainage is an important factor. And this software or this module also allows in order to do this. So this one is a part of it. B, sizing of detention facilities for flood control. Yes,
This is also.
this is also
Yes, yes. Application.
sizing of detention facilities. Okay, Vaishaka says yes, so let's mark it yes. Option C, floodplain mapping of natural channel systems. Is that a function? Yes, so
Yes.
yes, so you'll have to do floodplain mapping. That's in fact the preliminary step that we need to do. So it is a function. Now, last one, control strategies of minimizing combined sewer overflows.
Yes.
Yes, so in combined sewer design, we already saw how do we control. We can make it into a partially combined system in order to control. So all that. So A, C, and D are applications of SWMM, but B is actually not an application. So again, we need to size detention facilities, true for stormwater management, but this particular module or this software does not allow us to size the detention facility. Like we cannot plan the how much of the detention facility be, that planning we cannot do. So all the surface level things, like for instance, how is water flowing, what should be the drainage channel for that, what should be the sewer lines for that, so all that we can do, but all the detention facilities or you block it, so all that blocking or that we cannot do in SWMM module. So this is what we oh, sizing of detention facility is there. Okay, sorry, my fault. Sizing of detention facility is a is part of it. You were right. I think I got confused with another thing. So yeah, so I mean you can size, sorry, you can size the detention facility, but when it comes to other facility planning, pumping and all that, that you can't. In this sizing, I was thinking about that, my bad. Yeah, so all four, yeah, so it's correct, all four are applications of this one SWMM module. Yes, so any doubts in this question?
No,
Okay,
ma'am.
very good. Yeah, so let's proceed further. Question 8. The dash of a storm event may be defined as average recurrence interval between events equal to or exceeding a specific magnitude. Okay, so let's see. So it's a storm event, dash. So it's a period, obviously, of a storm.
Hydrograph.
Okay, so Partha says hydrograph. Anybody, any other guesses? Average recurrence interval between two equal events or exceeding a specified magnitude.
I think it is time area histogram.
Oh, time area histogram. Okay. Anybody, any other guesses? Okay, so the answer is return period. So return period of a storm event may be defined as the average recurrence interval between events equal to or exceeding a specific magnitude. So this we briefly discussed in our last week's lecture also. So where we said that like you have a storm event of intensity I. Now you look at after how long will this same storm event repeat, or something which is exceeding this I, something greater than I, after how long is it going to repeat? That is called the return. So it's the recurrence interval, average recurrence interval between events equal to or exceeding this particular magnitude. That is called the return period of a storm event. So this is by definition. So sometimes we fix the return period, like we say that, so based on this, we say that it's a 5-year return period for this particular region. So which means in 5 years, what is the intensity of rainfall which keeps repeating? So if you're fixing as 5 years, then which means like probably if the for this particular intensity, like around 10 mm rainfall is there in that 5-year period. This is something which keeps repeating. Whereas when you take it as a 10-year return period, maybe even higher intensity rainfalls might repeat in a 10-year. So we can even do that way where you fix the return period and you look what is the intensity which is being repeated. Or you can see, I want to see that this is the intensity that I want. Like I want to see around 10 mm. How long will it take for this to repeat? So then after that you can, so that might take 10, it can be a 10-year, it can be a 15-year. So you can fix either. So then we also learned duration. So intensity, frequency, duration graph we learned last time. So at that time we discussed briefly about this return period, how it would be there. So this is a definition of return period, that a return period may be defined as the average recurrence interval between events equal to or exceeding a specific magnitude. Now, what is design period if that is the case? This we have discussed. What is design period? Hey,
There's
this,
some
yes.
maximum of PS which sewage or any kind of structure to work. It should
Okay.
be
Okay.
functioning.
Correct, correct. Very good. Yeah. So it need not be fully for sewage. So this is a term which is used in anything, like any facility planning, it is there, or even infrastructure planning, it is there, where you say that. So if it's infrastructure, you say that that is the number of years, not the maximum, the minimum number of years for which that facility, that infrastructure should last. Here we are talking about facilities because water supply, sanitation, all these are facilities. So the design period in terms of facility is that for number of years for which this facility is designed for. So if you have a 30-year design period, which means for 30 years the facility should last, and after 30 years, even if it becomes redundant, it's okay because you're not designing it for more than 30 years. Like if we give a value like that. So this we have discussed, like for instance, if it is pumps, usually they have a design period of 15 years. And if it is other long-term planning, something, some facility like sewage planning, we usually say that it's for 30 years we designed it for. So we design based on that. So all the investment that we will be doing will be considering that this should work for 30 years. So this in our module 2, we have gone into in-depth discussion about this, where we went into what are the factors which influence design period, like population, land use changes. So when all these things vary, how design period is being affected, and we need to consider all this. So I think there were questions also based on that. So you might brush up that for your exam point for your examination, because it's a very important factor. So you may get questions based on that. So yeah, so that is design period. Now yeah, hydrograph. What is hydrograph? So hydrograph is if you have, so this is again used to find out, when you're calculating the surface runoff, stormwater runoff, we use different methods. So one method is where we plot a hydrograph. So hydrograph basically has the duration and the intensity of rainfall. So intensity again, intensity in millimeters, duration in seconds, and this gives us, so let's say for like 5 seconds, 10 seconds. So for every, so for 5 second duration, what was the intensity of rainfall? So usually when it is shorter duration, you say that maybe the intensity is high. Now for 10-second duration, what was the intensity? So you get a graph something like this. So this is a hydrograph which plots the duration of rainfall with the intensity of rainfall which was there. And the time area histogram converts this hydrograph into something like for every time, what is the, yeah, so we have it there. What is the area which is there? For instance, in the, so if you have a return period, which is, let's say the return period is t seconds, delta t. So for t seconds, what is the area uh, which is there? And for 2t, what is the area which is there? So like this, we keep plotting and we get a graph. So this is a time area histogram. So this again is used in, so why this is there is because imagine you have a catchment. So for one particular time, so let's say for T, maybe the water from this region flows to this region. It reaches only up to here. And for it to flow to this region, so this is the area segment. So an entire catchment is divided into multiple segments. So that is what we mean by area, like how much area of each segment is covered. So at time T, it might reach only till here, but at time 2t, it might reach till here. So you're plotting the path of the water and then based on that you're taking. So this will be clear when we discuss based on the discussion from the lecture. So this is the rainfall hydrograph. You have the duration, you have the intensity. So I think this is clear. So from 0 to 10 seconds, this was the intensity, and 50 to 60 seconds, like for this duration, you've got this much intensity. So which means this is the maximum, which is then again, as the duration increases, it is again reduced. So you're getting a hydrograph based on that. Now this is for time area method. One sec, slides. Yeah. So this is for time area method. So this is your entire catchment area. Now you're dividing that into different zones. So for that you use isochrones. So isochrones are any lines, or so it's basically a line, an imaginary line from which the time taken to travel would be the same. So you have for pressure you have isobars, then you have isotypes. So which means that everything is same, like, or the something is same. That's why it gets the term iso. So you have the isochrones, which means that the time. So all the water from this region will take this much amount, like from this region to this region, it will take 3 delta t, or if you're taking t as your time reference frame, 3 times as your unit, 3 times it will be taking. So that's how you generate a hydro time area histogram. So yes, so all these are used in order to find the intensity of rainfall, in order to calculate the total runoff which is there. So here the question I've been asked for, I mean this one is return period, but I just explained these because these are also important. Fine. Any doubts in this question? Okay, let's proceed further. Question 9 again. Return period selection of a storm depends upon which of the following? A. Importance of the drainage area. B. Socio-economic conditions. C. Constraints on funding and availability of space. D. Design period of infrastructure. Now that we have explained, we have discussed a bit on return period, I think you will be able to attempt this question. Okay, so let's go option by option. A. Importance of, is drainage area important for return period selection?
Yes, ma'am.
Yes. Why it's important? Because now again, if you have a drainage area, like you have 2 drainage areas. So again, what is return period? You need that much intensity of rainfall to repeat after that certain interval. So if it is a small area, then you can say that like I might get an intensity I. Whereas if it is a large area, so again, it depends upon your partial area effect also. Sometimes the, sorry, sometimes the intensity which I get from this small area for when there is high intensity rainfall might be more than the concentration or the overall intensity that I'm getting from this small area. So again, area plays an important role in your overall intensity that you're getting. So now that again, for the intensity to repeat, again, it depends upon the area. So the importance of drain. So return period selection depends upon the importance of drainage area. Correct. Now B, socio-economic conditions. Yes, no?
Yes, ma'am.
Yes, socio-economic conditions also. Why? Because your usage pattern depends upon your socio-economic condition. So, which means the overall amount of water which is going as surface runoff, amount of water which is going underground and which is used from the aquifer. So, all these depends. And based on the amount which is going as surface runoff, only will your return. So, basically, the same intensity has to repeat, right? So, to get the intensity, your socio-economic conditions are also important. Very good. Now see, constraints on funding and availability of space. Yes, so constraints on funding and availability of space also influences to an extent. Why? Because if you have certain constraints, then the usage pattern will also be restricted because of these constraints. So this again influences your socioeconomic condition. So when it comes to funding, the certain constraints, so these both are interlinked. So they both contribute towards your return period selection. Now the last one, design period of an infrastructure. Yes, no? Yes, no, anything.
I think no, ma'am.
Why? You're right. Design period does not influence, but why? Why did you feel that it's no?
Because if it is heavy rain and is happening,
Hmm.
it may happen like very high intensity at any 1 or 2 days, but other days it will be less.
Okay.
So that is a
Okay.
like
Yeah, so
the
that is
flow will
true.
be very less.
Yeah, that is true. Yeah, if it is high, then the frequency of that happening is less. Yes, that's a very valid point. But here, how does it affect the design period? If the frequency is less, how does it affect the design period? No, I'm trying to understand your reasoning. That's why.
Actually, risk analysis will be done. So
Okay.
based upon that, design will be not considered.
Oh, okay, okay, fine. Huh, that way. Makes sense. Yeah. So it doesn't because it's a very rare occurrence. So you're saying that in design period, okay, so you're going the other way around. In design period selection, the return period of storm event need not be considered, or the high intensity rainfall need not be considered, is what you're saying. Yes, it makes sense. But here the question is, for return period selection, do you have to consider design period? Which is an absolute no, because design period only talks about how long a facility lasts. And after that, if the facility is not lasting, you're going to design some other facility, right? So you need a facility, you're designing it for 30 years, and after 30 years it doesn't mean that you will be without any facility. You will design another facility at that time. So the design period and return period does not have any correlation. Like it's not like, especially return period is not dependent on your design period. Design period, as you said, can depend upon your return period also. So as rightly said, if it's a heavy intensity rainfall, yes, maybe it might not be happening always, but you need to have the average return period. You need to know at what frequency it is repeating, or what capacity for which you need to design the facility. So that capacity, again, not exactly for design period, but while designing the infrastructure, we do take into consideration the capacity, the average return period which is there, so that you can plan whether it would be the infrastructure is adequate enough to cater to that return period. So that is considered while designing the infrastructure. But for the return period, design period does not, like it doesn't have, like, this relationship does not exist. Okay, any doubts in this question? So this is what we had discussed, return period selection. So social importance of drainage area, socio-economic conditions and constraints, and yes, so that's it. Okay, so let's proceed on to the next question. Question 10. Okay, so it's a match the following. So inlet time, we need to match it with, so inlet time, travel time, time of travel, sorry, and time of concentration, partial area effect. So these are the things which are asked. So let's go. First one, time required by storm water in traveling from uppermost inlet up to the point of concentration. What is that? Is it inlet time, or is it travel time, or is it time of concentration, or is it partial area effect?
Ma'am, that is time of concentration.
Time required by storm water in traveling from upmost inlet up to the point of concentration. Okay. Okay. So let's say Pata says that is time of concentration. Fine. Then what is the next one? Maximum flow while part of the upstream catchment is contributing. This we have discussed before. And I think all of you have attended that class also. So maximum flow while only part of the upstream catchment is contributing. You should be able to answer this. High intensity rainfall in low area can lead to overall higher runoff than low intensity rainfall in a larger area. What was that called? Aishwarya, you should be able to answer this. No? Okay. That's a bit disappointing. So that's partial area effect, which we have discussed this in our previous classes. That's why.
Yes, I remember now.
Okay. Good. Yeah. So this you revise properly because gate questions and also for your NPTEL exam also, this partial area effect is usually something which keeps repeating. It's usually asked. So yeah, don't forget this. Okay, so then third one, time required by runoff from the most remote point of the catchment to flow across the ground surface and drains to the inlet of the sewer. What is that now? Any guesses? Yes, Partha, you were attempting this question.
Ma'am, I think that is inlet time.
Yeah, because inlet of the sewer, so it's the time required from the most remote point to flow across the ground to the inlet of the sewer. So yes, so that is inlet time, correct. Now comes the last one. Time required by runoff from the most remote point of the catchment to reach the point of concentration.
Time of travel.
That is time of travel. Okay. So, no, so you're wrong. There is some change. So let's see. Time of travel. So we have learned time of concentration is divided into two parts, is inlet time plus time of travel. Remember this? Remember such a relationship? Yes, no?
Yes.
So the first one is inlet time, which is time required from the most. So you have a catchment. So from here, now you have an inlet over here, and your a concentration uh, region or where you're taking the probably your rain gauge or somewhere where you're measuring is kept over here. So from this point till here becomes your inlet time, I. So which is this one. And
Okay,
then you have
then time of travel is option 1, if I'm not wrong. Time required by stormwater and
correct.
coming from the uppermost inlet.
Inlet up to the point of
Point of
concentration.
concentration.
Correct.
Fine.
So from the inlet to the point of concentration is time of travel, which is this. And from the most remote region to the inlet is your inlet time. And overall, this together, that is time required from the uppermost remote point. So now you're talking from uppermost remote point to this, the whole thing, to the catchment or point of concentration is your time of concentration. Okay. So what does that come up to? Which option? A3. Yeah, A3B. So option A, I suppose. Yes, any doubts in this question?
No, ma'am.
Okay, let's proceed further. Question 11. The right order of modeling steps in SWMM is. So yeah, so this is some memory question. So I think very briefly this has been discussed. So Let's see. So it said catchments and sewerage network and components are drawn from the study area. Simulation is conducted. Default options and object properties are set. Properties of the objects are edited as per existing or proposed design. Result. Okay, so this is another one, I think. Results of simulation are generated and E analysis options are chosen and F results of simulations are okay. So this is repetition. Yeah. So E analysis options are chosen and F results of simulation are generated. So let's see. Yeah. So can any of you attempt this question? What might be the first step? Like any order? Okay, so let's see. Anyway, results will be last one, so that's not going to be. Analysis options are chosen, so this can be an intermediate one. Let's see. So first we need to find what you're doing, right? So when you're modeling,
So A is the first one, ma'am.
A's of catchment and sewerage networks and components are drawn from the study area. Okay, A is can be a first one, but
First of all, the default options.
very good. Yeah. So first you need to set the default options. Default options and object properties are set. So you're taking the model. So you're making the model. You're opening the model. You're getting the default options. Yes. Very good. So what will 2 be?
Then we'll draw the catchments and sewerage.
Very good. Yeah. So what Partha said will go second. After you get the design, then you have the catchments and sewerage network. Very good. Yes. And now after that,
Properties of the objects are edited.
yeah. So before we start our simulation, now we need to edit the properties. So 3, yes, properties of objects are edited. Very good. Next. So now you put the properties. Yes, yes, very good. Next is, yes, very good. Analysis options are selected after that because now you've set the properties. Now you need to set what are the analysis options. So analysis options are chosen. Very good. And now, yeah, now these are easy. Last 2.
Simulation and then the results of simulation.
Very good. Yeah. So simulation and then you get the results. So that is what we saw here. Default option, catchment, yeah, sewerage network is drawn. Properties of objects are edited. Analysis options is chosen. Simulation is conducted and results. Okay. So we'll proceed on to the next question. Question 12. Choose the correct statement from the or statements from the following. A. Saturation near point of concentration influences the runoff more than the areas farther away. So we should have been here. And B. Longer periods of light rain corresponds to lower runoff coefficient. D. Rastral formula is the most popular method to determine stormwater runoff. Okay, let's go option by option. Option A. Saturation near point of concentration influences the runoff more than areas further. So you have a region, and this is the region where you want to find the point of concentration. So it's all flowing from this to this. And the point is, if you have saturated soil at this region, and if you have something over here, this influences the surface runoff more than the region farther away. Is that correct?
True, ma'am.
Yes. Why do you feel so?
Because that's going to influence on the amount of runoff that's going to come in the areas that are farther away.
Yes, very. Sorry, come again. It influences the runoff that is going to come from the areas farther away.
Yeah. Well, no, from the point of concentration.
From the point of concentration. Correct. Yeah. So yes. So if this point is saturated, then you won't have much runoff coming. And also, sorry, if this point is saturated, you'll have more runoff because by saturation, what do you mean? The ground does not have any more capability to hold water, which means whatever water is flowing will whatever rainfall is there, it automatically gets into the runoff concentration. So which means so now imagine the same region is not saturated and this region is saturated, which means from here whatever rainfall is falling, because it's saturated, it is coming. But since this region is not saturated, now this has the capability to hold water, So all that water will be lost over here, or majority of the water will be lost over here, and very less water will actually reach the point of concentration. So having at the near the point of concentration of the soil is not saturated, then the water in that travel time, while it's traveling through that region, it percolates into the soil and it goes as groundwater. So the runoff or the it influences runoff because of that. The actual runoff that you're getting reduces because of that. So yes, so this is the correct answer. B, longer periods of light rain corresponds to lower runoff coefficient. So I think we can give this question. Yeah, Partha, yes.
It's true, ma'am.
Longer periods of light rain corresponds to lower runoff coefficient. Yes, explain. No explanation. Hello.
Based on saturation point.
Saturation point. Yes, it is based on saturation point only, but I want to hear your reasoning for that. Okay, so fine. Vaishaka, do you agree to the statement? Longer periods of light rainfall corresponds to lower runoff concentration.
Yeah,
It's a
like
correct statement.
I think so, because then this percolation inside the ground while it's flowing will be there, and the evaporation, like many factors will affect, and then the runoff coefficient will reduce eventually. Like,
Okay,
uh,
okay. So let's see.
so,
Now, longer period. Okay, so let me ask Yatika, do you agree to the statement?
Ma'am, logically it does make sense ki, like if it rains, light rains for a longer period of time, so the coefficient might reduce. Whereas like if it's heavier, so I think it's correlated together, but I might be wrong, so I'm not really sure.
Okay, okay. Aishwarya?
Yes, ma'am.
Okay, so all of you have saying that this is right. Okay, let's now.
I think that is wrong, ma'am.
So let's discuss. So if
If
we
it is
have
heavy
a,
rain, it will be more
sorry, yes,
enough.
tell. If it is
I
heavy
think
rain,
this is the,
Okay.
then there will
If
be
it is,
a
yeah.
lower runoff coefficient.
yeah, so now all of you are changing. Okay, let me hear that
Yeah.
properly. No, I didn't get you. Can you give your reasoning once more, Partha?
Ma'am, if it is like heavy rain, then there will be a lower runoff coefficient. Ma'am, if it is like light rain, it will be higher. The
Why?
runoff coefficient.
Why?
Um, I
The
don't know exactly.
capability of the soil to hold water will be a factor, I guess.
Yes, it is a
Based
factor.
on permeability.
Yes, for longer duration, the capability of the soil to hold water will be much better than that of flash flood or a heavy rain.
Yes. Yes.
That is permeability.
Yeah,
Yeah, correct. 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 Both of you are correct. So the highlight here is that there is longer period also. So the initial reasoning which all of you said, where if it is light rain, then the runoff will be less. So that works if it's just a light rain for a small time, then okay. Your whatever rain is there, it's getting percolated, your permeability, and it stops over there. But longer periods of light rain, we have already discussed that when you have longer periods of light rain, what happens is that the soil gets saturated because of that. Because now, if it is heavy rain, then less amount of rainfall gets into the soil and more will go as runoff because it's heavy, so it's continuously flowing, so it doesn't saturate much, it just goes as runoff. But if it is flowing very slowly for a long time, then it gets into the soil. So because it has time, the permeability takes time, no, so it has more time to penetrate into the soil and then get in, so the soil gets saturated because of that. Like it's possible to saturate the soil because of that. Now if the soil gets saturated, then whatever rain which falls, which means it's already saturated, which means it's like block done. So there will be more runoff. So your runoff coefficient will be higher for longer periods of light, longer. So again, the catch here is it's longer periods. If it was just light rain corresponds to a low runoff coefficient, maybe you were right. Like it can lead to that. But longer periods of light rain corresponds to higher runoff coefficient. And if it was heavy rain, then it would have been lower runoff coefficient. That also we can be there. Okay? Yes,
Yes,
no?
ma'am.
Okay.
Yes.
Last one. Rational formula is the most popular method to determine stormwater runoff.
True, ma'am.
True. This we have discussed. We have discussed multiple methods like time area method, unit hydrograph method. So all these we have discussed, but rational formula RCIA by 360, that's the most popular method. We usually use that because it's very convenient to do it that way. Right. So what is the answer for that? So A and C. So option C, A and C. Right. So let's see. Yeah. So this is what we discussed. So if it is longer periods of light rain, it saturates the soil and hence higher runoff coefficient. But if you have heavy intermittent rain, again, if it's heavy continuous rain, it changes. If it's heavy intermittent rain, then intermittent, you mean it's not steady, like it rains for some time and then there's no rainfall, or it's a very low intensity rain, then again high intensity rain. So usually high intensity rains happens that way that we have discussed. It's therefore very short durations. So yes, so in that case, it can be a lower coefficient because there would be less saturation, because whatever is there, it immediately goes as surface runoff. It doesn't get enough time to saturate the soil. Okay, so let's go to the next question. Question 13. Runoff entering into the sewer depends upon which of the following? A. Imperviousness of the catchment. B. Shape of the drainage area. C. Duration of storm. D. Specific yield. So let's go option by option. Imperviousness of the catchment. Does the runoff entering the sewer depend upon that? Yes. Does it depend upon that?
Yes.
Yes. Be
Yes.
confident. Yes, it does. So this is what we have been discussing all this while, that if the soil is more impervious, by impervious, which means the permeability is less, which means water doesn't go down, which means more runoff will enter into so this is again just by talking about entering into the sewer, which means so the sewer can be placed in your so it can be the inlet point. So you have something, if this is your pipe, so it can be the inlet point, the point of concentration. You can keep a sewer in your point of concentration, if that can also, like for instance, the inlet and your point of concentration can coincide. So whatever it is, from this point water has to come to this point, so which means the permeability is a factor over there. So this option is given in such a way that it's not directly talks to you about permeability, but it just talks about impermeability. It's not even talking about porosity. It's just saying that imperviousness of the catchment, which essentially talks about the porosity of the catchment, that it is not porous or it's imporous. So yes, it influences. Now B, shape of the drainage area.
I think yes, ma'am.
Yes, because by the shape of the runoff entering into the sewer will depends upon the shape, how you have placed it, or the slope in which you have placed it. Otherwise, it'll be difficult for water to enter. You're placing it up, or you're placing it in a rectangular form where water is coming this way, or imagine you're placing it in a triangular form and water, it doesn't get in easily. So based, or if you have the runoff like this, you just dig something and then you place a circular conduit, something like this, it might be more easier for water to get in. So runoff entering into the sewer depends upon the shape of the drainage area. Yes. Now C, duration of storm.
Yes.
Yes. Yes.
Yes, because the intensity again depends upon the duration. There's an intensity, duration, frequency relationship, and based on duration, saturation can happen. All that, whatever we discussed before. So all that comes into play over here. So yes. Now last one, specific yield. What is specific yield? We might have to go back to our module 3 where we discussed about groundwater aquifers and we discussed about specific yield of groundwater over there. So it mainly talks about the capacity of water, the capacity from or how much water can be taken from the aquifer or the yield of a well we discussed. Like if these are the conditions, find what is the yield. So yield means how much can be extracted. So that is for that well, and specific yield means from that particular aquifer or from that particular soil how much can be yielded out. So this again mainly talks about how much we can get from that water facility or from that water source. So the runoff entering into the sewer does not depends upon your specific yield. So this is not there because this is a property, like it's a property of the aquifer, it's a property of the soil. Like sometimes the soil, the water holding capacity of the soil influences the yield. So this all comes under the property of that, but the runoff entering the sewer does not depend upon the specific yield. So that is A, B, and C. Any doubts in this question? Okay, let's proceed to the next. Yeah, so this is what we discussed. So yes, so imperviousness of the catchment, it depends upon the land use, the runoff coefficient, shape of the drainage, duration of storm. So this, I think this slide was already shown to you before. So now specific yield means the measurement of water removed by the aquifer by force of gravity to the well. So this is how much you yield out from that. So you can remember that way, like what are you yielding out from that. So what is removed from the aquifer through gravity discharge or even through pumping, like what are you pumping out from that. So that's what you talk about specific yield. Now question 14. Determine the minimum required diameter of a circular sewer making use of the following data. Area to be served. Okay, so this is a calculation. So what we have to find is we have to design a circular sewer and we have been given area to be served is 120 hectares, population 50,000, permissible velocity is also given for 3.4. So before diameter was given in the previous numerical, we had to find what is the velocity. Now velocity is given, we need to find what is the diameter. Now we are also given the time. So we discussed, we have an inlet over here, time of concentrate, like point of concentration is here. So we have two times, the inlet time, travel time. So you have time, inlet time given to be 5 minutes, travel time given to be 20 minutes. So your overall time of concentration will be 25 minutes. So that we can combine and we can say 25 minutes. Now rate of water supply is 230 liters per capita per day. Impermeability factor is also given. So now we have to design this sewer. So by default, we're assuming that it is a combined sewer because we are designing both stormwater and it's a combined sewer. So which means when you're designing, so the capacity of the sewer, you'll have to find what is the stormwater discharge or stormwater which will be there, plus what is the sewage discharge. So these two will have to be there. Like in order to find the quantity of water which is required, we'll have to find this. So because it's a combined sewer. So in the question, it's not given, is it? Okay, it's not given, but this kind of question is usually asked where you're given entry time because this is a runoff time which is given, and you're asked to find the sewer design. Like otherwise, it would have been like just surface runoff pipe or something like that would have been there. So you can keep that in mind. Sometimes it can get tricky because they've asked to design a sewer and because all the runoff details are given, it is a combined sewer that they're talking about. If it's not, it would be separately mentioned in the question. So yes, so in this, now let's find what is the stormwater. So to find stormwater discharge, we know in order to find the volume of stormwater, we use CIA by 360, the volume of water which is there, or discharge, yeah, quantity of water, Q, CIA by 360, which we use, where C is the this one coefficient, and I is the intensity, and A is the area, which is the area of the catchment that we are talking about. So in this, A, we know the area of the catchment, so area to be served is 120 hectares. Area we know, but we do not know what I is. C also we know the permeability factor is given, so C is also given, but we do not know what I is. How do we find I? So to find I, in the last lecture, we learned one formula. It was 25.4 into A divided by T plus B. Remember this formula? So where A and B, A is equal to 30 and B is equal to 10. If the duration lies between 5 minutes and 20 minutes, duration of the storm, and A is equal to 40 and B is equal to 20 if the duration is between 20 and 100 minutes. So here, which one will we use?
Second one, ma'am. A is
Second
equal to
one.
40.
Yes, very good. Because it is 25 minutes, so we will use A is equal to 40 and B is equal to 20. So let's do that. First, let's find the intensity. So I is equal to 25.4 into A is 40 divided by 20. Yeah, so time is 25 minutes. We have got it here. So 25 minutes plus 20, which is B. So how much does that come out to?
22.55. 22.57.
Yeah, so 22.57. Very good. 22.578 something will be there. What will the unit of this be?
mm per hour.
Mm per hour. Okay, let's look back over here. What do we have over here? So these are all constants, right? And then you have T over here. Okay, so from this I think you can't, but intensity is no. Intensity is in it's not in. No, it is just millimeters because you're talking about the
Oh,
intensity. It is,
millimeter, just
yeah, there is
millimeter.
no hour over there. I was just looking whether that hour is getting cancelled somewhere. No, it is not there. The intensity is just in millimeters. So it can, so this is something which you need to keep in mind. For rainfall, when you're measuring rainfall intensity, even though you want to find the discharge, you want to find the volume, everything, the unit of measuring rainfall is always millimeter, or height is used in order to maintain measure rainfall. So this is again a popular question which is asked in all these examination, because you're talking about rainfall. Mainly, we always think that it's in volume or meter cube or it's in per hour. Like we always tend to make this confusion. But no, for rainfall intensity, it's always measured in rain gauge. Also, we always measure the height or the millimeter. That is the unit of measuring intensity. So yes, so this is intensity. Now Q is equal to CIA by 360. So let's find. So I permeability factor 0.45 into I 22.478 into A, which is what is your area? Yeah, 120 hectares. So I'm not converting hectares, I'm leaving it as such because in our 360 it's already taken care of. That is the factor that we're getting over here, because some textbooks might not show this 360. It would just be CIA, which means we'll have to convert everything. Like you'll have to convert this into hectares, then some minute conversion is also there. So yeah. So how much does this work out to?
3.38. 3.38.
3.38, very good. Yeah, 3.38 meter per second. Yeah, very good. Now that's about so this is one part. We have got storm water. Now we need to find the sewage which is generated. So we have, so again, in sanitation studies where we calculated how much of sewage will be generated, we saw how do we do this. So let's just recollect that. So we have 230 liters per capita per day is the water which is supplied. So let's see what is the supply. It is 230 liters per capita per day. So and we know that the population is 50,000, which means for the entire locality, how much will the water supply be? 230 into 50,000. So per day, 230 into 50,000 will be there. So these many liters of water would be required per day. So now how much will be, yeah, so let's just see. So this is one thing. So now liters per capita per day. Now we are interested to find in liters per second, like so this is per day again. So per second, how much of water is being, so again, why? Because here we are calculating meter per second, the volume which we are, the discharge which is there, it is in meter, sorry, meter cube per second. Meter cube. It is in meter cube per second. Now, eventually, this also we want to find it in meter cube per second. So now we have it in liters per, so per capita we removed by doing into 50. Now per day also we need to remove. So to convert it into second, what will we do? We'll have to, so it is per second. So we'll have to divide this whole thing by 24 into 60 into 60 with me. Is that clear, right? How we are doing that? Because it's day, you have to convert it into second, which means you need to, and it's per second, like which is already in the denominator. So you are actually multiplying it in the, like you take the reciprocal, so it eventually becomes this way. Okay, how much does that work out to?
0.133 meter cube per second.
0.133. Okay, can you just 0.1, yeah, 0.13, yeah, correct. So it is around 133 liters per second, which when we convert to meter cube, it is 0.13 meter cube per second. Very good. Yeah. So now we have to add these both, 1 plus 2, which would be 3.38 plus 0.133. So that is 3.5 something, right? 3.58 something it would be. Okay. Everybody here with me till here? Q is equal to 3.58.
Yes, ma'am.
Yes, okay. Thank you for the confirmation. So now we have got Q. So again, going back to the question, we need to find what is the diameter, right? Yeah. What is the minimum required diameter? So going back the previous one, Q is equal to AV, V is equal to Q by A. Sorry, A is equal to Q by V. So Q we already found 3.58 something divided by V. What is V? V is already given in the question, 3.4 meter per second. So let's go back, 3.4. So yes, so A is equal to 3.58 divided by 3.4, which is pi d square by 4. D is what we are interested to find. So d square is equal to 4 by pi into 3.58 divided by 3.4. So how much does that work out to? And what is d?
D is around 1.1 meters.
D is around 1.1 meter. Correct. Yeah, D is around 1.1 meters. 1.15 is what we are getting. So we can approximate it to 1.2 meters. 1.1, 1.2, both are right. Okay, did everybody get this answer?
Yes, ma'am.
Yes, ma'am.
Okay, very good. So then we can proceed further. Yeah. No doubts in the previous question, right? Shall we move to the next question? Just a quick confirmation.
Yeah.
Aishwarya,
Yes,
can we
ma'am.
move? Okay, very good. Yeah. So question
Yes,
15,
ma'am.
choose a correct statement regarding the time area method from the following options. It is an extension of the rational method. This method uses effective rainfall and computing sub-area. It can account for the temporal variation of rainfall intensity and could be applied to mid-sized catchments. It is based on the concept of unit hydrograph. So let's go option by option. Time area method. So they've asked about time area method. So we briefly discussed this before. So we saw that how a catchment is divided into different sections. We take how much time it takes for water to flow from one point to one section, which these are the isochrones, and how much time it takes to move to one isochrone to the next isochrone. And looking at that time, we take T, 2 times delta T, and then we plot and how much area is being covered. Like so, we make an area plot. So how much area is being covered in each time, and we make that plot. So based on this, we get how much, what is the runoff which is there in that particular area. So this is time area method. So option A asked, is it is an says it is an extension of rational method. Is this true or false? Is it an extension of rational method?
I think true, ma'am.
True, it is an extension of rational method. So only difference is that, so in rational method you have like So rational method, you have CIA by 360. So you're basically here you're dividing it into multiple small regions, and then you're taking it. So I mean, instead of directly using this formula, the same method, the rational same method is being followed over here, where you're taking the area, like you're separating it into area, and for each area you are finding what is the time, how much time, what is the intensity which is flowing, and you're plotting it. So this will give us more accurate results compared to the rational method. So it is an extension of rational method, yes. Now this method uses effective rainfall and contributing sub area. Yes or no? Yes, so this method, so why? So you have the effective rainfall area, which is your overall area, and then you're subdividing it. How much time? So this is the contributing. So this sub area is contributing this much. This sub area is contributing this much after that. Then this is, so that's what. So the effective rainfall and the contributing sub area is taken. So which means whatever is there from, so by effective rainfall, which means that whatever has been there till then. So if I'm taking this point, whatever has been till here is the effective area, and now this contributing sub area, so it essentially adds the effective rainfall and the contributing sub area. So this is correct. This method uses effective rainfall and contributing sub area. Now see, it can account for temporal variation of rainfall intensity and could be applied to mid-sized catchments. True or false?
Think true.
Yes, it is true. So it can account for the temporal variations of, why? Because now you're again same thing. You're dividing it into multiple segments, which means you can account for the temporal variation. By temporal variation, we are talking about with time, how is there a variation. So that is what you're doing over here for each time, how much of volume of water you're getting. So it is accounting the temporal variation of the intensity of rainfall. So for all the intensity, how much time it's taking. So it does account this, and this can be applied to mid-sized catchment. That is what we are doing over here. That is true. And last one, it is based on the concept of unit hydrograph. Is that right?
No, ma'am.
No, this is a different method. This comes under the unit hydrograph method. Like there's a separate method which is based on unit hydrograph. So what that does is you take a unit area and then you see how much of rainfall is falling, or the intensity of rainfall, which is like in millimeter, the intensity of rainfall. So for a unit area, what is the intensity of rainfall? And based on that, you calculate how much would be the runoff for all the areas. Like, so it's a method that you use that way. So yes, so coming to this one, A, B, and C are the answer for this. So question 16.
Excuse me, ma'am.
Yeah,
Hi. So I have a doubt in this question. So a similar question is given in this week's assignment.
okay.
So another point written over here is time area method transforms a storm hydrograph into a runoff hydrograph.
Hmm.
So since it's like based on time area histogram, I think this is wrong. But
Okay.
could you explain this point?
Yeah, but that is given in this time's assignment, no? So I can't say whether it's right or wrong.
Mm, Okay, no. I know that that is wrong, but then could you
Okay.
like explain the point that it mentions like uh, the
Okay.
storm hydrograph and runoff hydrograph?
Okay. So I'm just going to that. I think I had the slide over here. Yeah. So this is your rainfall hydrograph. So this is
Yeah.
what, so you have duration on the x-axis, and then you have the intensity, like precipitation, on the y-axis. So this is in millimeters. So this is what we have been discussing. So for each duration, how much of rainfall you're getting in that particular area. So we make a hydrograph. So this is called a hydrograph. Now this hydrograph we converted into a hydrogram, where you plot the, so do I have it here? Yeah, so this is a hydrograph, and then you can, yeah, so this is a hydrograph. So from this you can develop a hydrograph by plotting the discharges against time. So this is intensity against time. Now you can even plot discharge against time, and if you plot the, so by discharge, again it is Q. So this is I by T, which is a hydrograph which we saw in the previous one. Now if you plot Q by T, it becomes a hydrograph. And this hydrograph, we convert it into time and area. How? So, so you know this one. In delta T, what is the intensity of rainfall which is there? Now you're looking at the area. So here you have the area. So in this area, so let's say we are starting from this point. So in time, okay, let's, which points time have they started from? So let's say the in this particular, so from here, let's say from A4. So from A4 in this, no, it is coming to this. So this is the point of concentration that you're talking about. So first it flows from here, and in this particular time, this much amount of water intensity is coming. So this is one isochrone. Then in another time frame, this much amount of intensity is flowing. So in time t, delta t. So sorry, I'm doing it the other way. You need to take it from this side. Let me just explain it once more. You need to take it from this side. So you have time t. So in that time t, so this arrow is shown in this way because in that time t, there are, like, from different regions water is flowing, right? So I mean, let me not confuse you with this, but let's just take the time area curve. And in time t, if there might be certain amount of intensity of rainfall which is there, and in time t2, whatever was there before plus from that particular area. So let's take this area. So this area, so in that time t, whatever was there before plus whatever is there right now gets added up. So like this, we keep adding, and we get the cumulative time. We get the cumulative area. So finally, so that is why these arrows are given this way. Finally, when you take this area, for all the areas, you add it up and then you get a time area curve. So this is our time area method. So now using this, we can find what is the intensity of rainfall which will be there in one point. So you're splitting it, you're segregating it into multiple regions, and you're taking, so in one region, what is the intensity which is there? What was the intensity which was there in the previous region? You're adding them up and you're getting it. Okay?
Yes, so ma'am, so in the time area method, we'll continuously add the previous ones
Huh.
again and again, but
Huh.
in the hydrograph one, we'll just take into consideration the changes that we're getting per change of the time, right?
No. So hydrograph also, see, so in hydrograph also, no, the difference in hydrograph and time area method is that time area curve plots the area, whereas hydrograph plots the intensity. That's it. So
Okay,
even
okay.
here it is in time delta t, what is the intensity? In 2 times delta t, what is the intensity? So you're at, so you have the, like, so here this one has only this intensity. Agreed. But yeah, it's not a cumulative
So
graph.
that's what I was saying.
Correct. It is not a cumulative graph. It is a separate graph. But if you're plotting a hydrograph, like when you're taking, then it becomes cumulative because for each one, what is the volume you're getting? So you can plot a cumulative graph also. So, but in a hydrograph, it is independent. Yeah, it is not cumulative. This one is a cumulative. This is not cumulative. Correct.
Okay, thank you, ma'am.
Yeah. Okay. So where were we? Yeah. So this is what we were discussing, right? Okay. Let's go to question 16 now. Unit hydrograph. Yeah. So there are different terms: unit hydrograph, lumped model, distributed model, and non-linear reservoir method. So let's see. One considers individual subbasins as a single unit. Average value of the watershed characteristics are taken. What is that? Which model considers individual subbasins as a single unit? Is it the unit hydrograph method, lumped model, distributed model, non-linear reservoir method?
Lumped model.
Lumped model, very good. Lumped model considers individual subbasins as a single unit. And next one, based on direct runoff resulting from a unit depth of rainfall, excess occurring uniformly over the catchment and at a uniform rate for a specified duration. Okay.
Unit hydrograph method.
Very good. Yeah, unit height. This is what we just discussed. So it's based on direct runoff resulting from a unit depth of rainfall, excess occurring uniformly over a catchment and a uniform rate for a specified duration. Very good. Now, third one, used for estimating runoff quantity for single event or long-term simulation of runoff, mainly for urban sub-catchments.
Non-linear.
Non-linear reservoir method, yes, very good. And then subdivides each sub-basin further into smaller cells.
Distributed
Distributed.
method model.
Very good. So this, I think, what is lumped and distributed, I think there's a question in this time's assignment. So none of you should go wrong in that. So yes, so that works out to option P2 and yeah, option B. Okay, so is that it? Yeah, that's it. That's all 16 questions. That's all for today's discussion. So if you have any doubts, you can ask now. No doubts?
Excuse me, ma'am.
Yes.
Ma'am, you know how like we have the English transcripts PDFs available for the lectures, right?
Yeah.
So yeah, so the PDFs for lecture 42 to 45 for this week
Huh.
and 48 for the next one are corrupt. So is it possible to get them somehow?
By corrupt, what do you mean? Like it's bad characters?
No, when I open it, it says that the PDF is empty, so you can't open it.
Oh, okay. So this, yeah, let me make a note of this. Which all are corrupt because this nobody had informed this before. Which all are corrupt?
42, 43, 44, 45, and 48.
42, 43, 44, 45, and 48. Is it?
Yeah, 48 is next week though.
Okay, but still, yeah. Okay,
Yeah.
so these are corrupt, and how do you do? Do you download and then try opening it?
I did both.
Okay,
I tried opening it in the drive. So it won't open. It says like couldn't preview file. The file is empty. And
oh,
when I download it, I'm just not able to like open it. Sometimes it's not even visible, the
oh,
file name.
okay,
But yeah,
okay,
that's the problem.
okay. I'll inform the NPTEL team. So we have a separate data uploading managing team. So I think they'll have to sort this from their end. So I'll inform them this.
Thank you, ma'am. Would it be possible to get it done before Wednesday so like I can also upload the assignment?
Oh, I'll mail them. Let's see. You can
Okay.
also. So I'll say one thing. Put this up in the discussion forum also
I
because
did. I
you
did in the
did.
morning. Yeah.
Okay, today, huh? Fine. Because I mean, yesterday I checked and I didn't see anything. That's why I was wondering. Okay, so then I'll also tell them. So it will speed up because of that. If students also put in the discussion forum, then they'll speed it up.
Okay. Thank you, ma'am.
Okay. So any other doubts or concerns? Nothing. Okay. So it was a long class today. We had so many questions to discuss. I hope assignments are fine and you're not finding them too difficult and all. It's okay. I think next week 11 and 12 onwards, numericals will reduce. Like it'll be more theory, so it's okay. It won't be difficult. Okay, so if that's the case, we can call it a day. Fine. Okay, thank you.
Yeah.
Yes, ma'am.
Yeah,
Thank you.
great. Thank you all for joining and thank you for being interactive. Looking forward to next week's session. So, yeah. Bye bye.
Thank you, ma'am.
Thank you, ma'am.
Good night.
Good night.